Hello, this is Dr. Gardner. Today we're going to be talking about conditions that affect reaction rates and trying to understand chemical reactions in a little greater detail. In our future tutorials after this, we will also look at chemical equilibria. So first of all, let's consider what are the conditions that can affect the rate or the speed of a chemical reaction. First of all, temperature tends to affect how quickly a reaction can occur. For example, temperature tends to relate to the kinetic energy component of your chemical reactions. And so if we consider that, the kinetic energy of our reactions can be related to a simple equation. So kinetic energy of the particles we're looking at in our reaction is going to be equal to 1/2 the mass of the particles that we're looking at times their velocity squared. Okay, so if we look at that kinetic energy, we can realize that this is going to be proportional to temperature. So as my temperature were to rise, the average velocity of my particles also will increase, which results in additional collisions, and every collision potentially can result in my reaction proceeding forward, especially when I'm dealing with several reactants that need to be combined in order to form products. Now, another effect that will relate to the number of collisions is the concentration of my reactants. So if my concentrations of reactants are increased, if I have more reactants in a unit volume, let's say in a water-based solution, my molarity, the concentration of the solute, if it were to increase, well, that results in increased collisions as well, which can also increase in increased reaction rates or speeds. Now, surface area. If I have more surface area, that gives some more sites for collisions to occur in order for products to form. So surface area, as it increases, also increases the rates of your reactions. If surface area was to decrease, it would decrease the rates of your reactions. So this is why it would be important to try to grind powders up into fine powders that you would use in a chemical reaction to increase that surface area. It would also increase how quickly they would dissolve in a solvent system. If I have a catalyst present, well, what this actually does is it provides a secondary pathway through which a reaction can occur, and a catalyst will change what we call the activation energy of the chemical reaction. And in many cases, we'll have what's called a positive catalyst, where the activation energy of the reaction is decreased, which can result in more effective collisions so that we end up with having products form more readily and more quickly. Realize catalysts, though, change the entire reaction pathway, though. Now let's consider surface area and how surface area can affect the rates of my reactions. Let's go ahead and heat up an iron nail, and we're going to put it in a bottle that contains pure oxygen. Now the concentration of oxygen is very high, which you would expect would increase the rate of reaction. By heating up the nail, we're also increasing the rates of our reaction, but the rusting of the nail is still less than if we had increased surface area. So let's say we were to heat up a piece of steel wool and place it inside the bottle with oxygen present. We would find that the steel wool would react much more rapidly, as we can see from the exothermic process of the wool rusting, and we can see sparks as that's occurring. So oxygen is combining very readily and very quickly with the iron, so we have a much faster chemical reaction with the increased surface area of the steel wool. Now catalysts are interesting because they do provide a secondary pathway for a chemical reaction. There's a very common catalyst called the catalase enzyme, which in biology will provide a secondary pathway for hydrogen peroxide to go through decomposition. What happens is the decomposition of the hydrogen peroxide will happen very quickly, and as that occurs, we can actually see on this piece of liver that we have here that the hydrogen peroxide is decomposing rapidly to form water and oxygen gas, which is the bubbles that you are observing. Now the catalase enzyme is lowering the reaction activation energy so that we end up producing products much more quickly. Now, in order to understand some of the other factors that are affecting how reactants will collide and form products, will involve collision theory. If we can think about collision theory and try to visualize our reactions at the molecular level, we can realize that as a reaction occurs, we must have reactant molecules that will collide. So this is why at higher temperatures we would have more collisions. That's required for our products in most cases, as well as at higher concentrations. But not only do we need a collision, but we also need proper orientation in many cases during our collisions so that bonds may be formed or broken in the proper locations. We also need a collision with enough energy to overcome an activation energy barrier in order to go forward to form product. Now, only a small fraction of the collisions that we have will meet all of these requirements of proper orientation and having high enough energy. So many times we will have what are called ineffective collisions, where the molecules or particles would collide, rebound, and not form any products. So let's consider a case where we have ozone reacting with nitrogen monoxide to form oxygen gas and nitrogen dioxide. As that's occurring during these collisions, we can expect that we must have proper orientation to form products. So here I have two examples of some possible collisions that could occur, and we need to decide which of these would form products most readily. Well, I know when I form my product molecule of nitrogen dioxide that I'm going to need to have nitrogen in the center with a bond to one oxygen and bond to a second oxygen. If we draw the Lewis structure, you can see that very readily. But in order for that to occur, then we really need the nitrogen to be oriented so that it will collide with an oxygen from the ozone to have an effective collision. If we have two oxygens collide, this would be an ineffective collision because we would not form a bond on the nitrogen that we need to form nitrogen dioxide. So this would be the choice for our effective collision in the second scenario. Now, when I'm looking at reactions, some reactions are considered endothermic reactions and others are considered exothermic reactions. An endothermic reaction has reactants that as they proceed from the beginning of the reaction to the end of the reaction, as they go from reactants to products, the products are going to end up at a higher energy. An endothermic reaction, we actually store energy in the chemical bonds that we're forming in order to form those products at their higher energy end of the reaction. Now, there are other exothermic reactions where reactants go to products that are lower in energy at the end of the reaction, in which case they give off energy to the surroundings. That's an exothermic process. If energy must come from my surroundings, then I'm going to have an endothermic process. Now, a lot of times what might be driving an endothermic reaction to be spontaneously occurring is increase in entropy in the universe or disorder in the universe with respect to the products that might be forming. So there are reasons why this happens thermodynamically, but we won't be focusing on them in this course. Now, if I look at a chemical reaction, let's say we're looking at ozone reacting with nitrogen monoxide, and that we have a collision where we end up with nitrogen colliding with oxygen in order to have an effective collision where I can start to form a new bond and break an old bond. And I have enough energy in this collision to overcome what we call an activation energy, which is shown here. If all of these are occurring correctly, then we can go ahead and potentially form products. That's my oxygen gas and the nitrogen dioxide. Now, since my products are at lower energy than my reactants, I would say this is an exothermic reaction. But we have to realize that we have to have a collision that's in the correct orientation. We form what's called an activated complex as those bonds are breaking and forming in order to form our products. So what I've shown you here is a reaction progress diagram, or sometimes called a reaction coordinate diagram, as I go from reactants to products as I progress from left to right and as I have energy on my y-axis. So as we're looking at this, this will help us to understand a variety of different chemical reactions and the types of activated complexes they form and the activation energies they must overcome. So let's consider what a catalyst would do to an energy diagram, such as this, or a reaction progress diagram, or reaction coordinate diagram. When I have a catalyst present, I will actually have a secondary pathway. So the original reactant to product process in an exothermic reaction might occur on this red line. We would form a transition state, and that transition state would involve proper orientation of a collision as we start to form or break bonds, and then we go to products. Now, a catalyst will provide a secondary pathway. In some cases, a catalyst might have a pocket where my reactant molecules may fit into the pocket and orient themselves in the right positions in order to form or break bonds to form products, and it might actually lower the activation energy as I'm showing here. In the first case with the red line, my activation energy was this entire distance, whereas my activation energy with the catalyst is a lower amount of energy. And I actually form not just one transition state, but I end up in this little pocket between the first and second transition state. For the catalyzed reaction, I form what's called an intermediate complex. So I formed an intermediate that is less stable, but lasts for a longer period of time, has a longer lifetime than the transition states would have. In some cases, we can actually capture intermediates and observe them much more readily than we can capture transition states, which have very short lifetimes. Now I have a secondary activation energy for the second part of this process. If I overcome both of these activation energies, we can go from reactants to products, and since the activation energy is much lower than the uncatalyzed reaction, the reaction speed or the reaction rate is increased. Now realize that catalysts aren't considered a reactant or a product. In fact, if your catalyst is functioning in a proper fashion, we would expect that it's not permanently changed during the reaction. So the catalyst may be involved with interacting with reactants to form products, but it should be regenerated at the end of the process and not used up. So we can say catalysts are recycled during a reaction so that they can be used over and over again to lower the activation energy for the reaction we are observing. So they should last quite a long time. Now there are cases where catalysts can potentially decompose with time, or their surfaces may be poisoned with contaminants, but until those things were to occur, the catalyst would keep being recycled and used over and over again, and that can result in a number of times that the reaction is catalyzed, is sped up by lowering activation energies by changing the reaction pathway. Now let's see if we can look at some chemical reactions and identify if I have catalysts present, or if I have intermediates that are formed but then consumed in the chemical reaction. Okay, so let's say that we have chlorine atoms in the form of CF2Cl2 that are catalyzing the decomposition of ozone. So this is going to be dealing with a chlorofluorocarbon. Okay, in those cases, what tends to happen is we produce free chlorine, monatomic chlorine in the upper atmosphere, which can catalyze the decomposition of ozone into diatomic oxygen gas. Now let's see how this can happen. The monatomic chlorine can react with ozone to form chlorine monoxide and diatomic oxygen gas. So the chlorine monoxide, though, is consumed in a secondary step. If I see a molecule that is formed but then is consumed, we would say that is a reaction intermediate. So this is going to be our intermediate. Something that is formed and then consumed. If I'm thinking about my reaction diagram, my energy diagram, if I'm looking at a reaction, the uncatalyzed reaction might look like this. The catalyzed reaction, as we were seeing before, might look a little bit like this, where we ended up with the reaction intermediate formed here. So that could be the chlorine monoxide that we could argue was forming. Now the catalyst isn't used up, so the monatomic chlorine is involved in the first step, but it's regenerated in the second step so that it can continue on and be recycled to destroy ozone over and over and over again. This is why chlorofluorocarbons can be so dangerous in the upper atmosphere and damaging our ozone layer, which is Earth's natural sunscreen to block portions of the UV radiation from our sun. Now we can see if we were to add up these two steps, since the intermediate is formed but then consumed, it's going to be present on both sides of my chemical reaction. So a lot of times it'll be left out since it's present there before and after, or in this case since it was formed and then consumed. So we usually will leave that one out. But we can see that ozone reacts with chlorine to form diatomic oxygen, and the chlorine's reformed. So the catalyst is present before and after the chemical reaction. So in all these cases, if I were to remove the intermediate and remove the catalyst, we can see that the chlorine monoxides are formed, and step 1 is an intermediate. It's only formed temporarily, but the overall reaction is only forming diatomic oxygen in a sped up process where the reaction rate is increased. Okay, now if we were to look at the catalyzed reaction, realize that we have two transition states. So this is my first transition state, and this is my second transition state. That is as it forms our intermediate, which is located here, which has a longer lifetime than either transition state would have because it is in a pocket of lower potential energy. okay, is lower energy than the two transition states. So that intermediate was like the chlorine monoxide that we just saw in the example of the decomposition of ozone by chlorine, monatomic chlorine in the atmosphere. Okay, so keep that in mind. Now, as we consider the decomposition of hydrogen iodide, it's an exothermic reaction, and as hydrogen iodide is decomposing, we form hydrogen gas and iodine gas. Okay, what I would like you to do is pause the video, and with your local instructor, I would like you to try to draw an energy diagram to show the uncatalyzed reaction. Okay. When you draw this diagram, I would like you to label the reactants and the products and realize this should be an exothermic reaction, so make sure you've drawn your energy diagram, your reaction coordinate diagram correctly in order to show the exothermic process. Okay, then I might want you to try to draw a possible activated complex that could be occurring as we have a collision between the two hydrogen iodide molecules. Try to show dotted lines to indicate energy changes in these cases. Okay. What we're going to do, though, is see if we have a platinum metal present, it will catalyze and increase the rate of reaction. So go ahead and show me a dotted line that indicates the reaction pathway when we have the catalyst present. Realize this will change the reaction path for the entire process as we lower the activation energy. I'll give you a hint. 2 activated complexes and 1 intermediate should be forming in your diagram. Okay, so go ahead and try that. Okay, so if you tried to draw your activated complex, since we're going to have hydrogens and iodines forming products, one possible activated complex could be a sideways collision between 2 hydrogen iodide molecules. So you might have tried this, where we start to form a new covalent bond between 2 hydrogens to form my diatomic hydrogen products, and we might be forming a covalent bond between iodines to form the diatomic iodine product. So that's one possible transition state or one possible activated complex that you might have tried to draw. Okay, now if you had drawn your diagram correctly, you may have drawn something like this, where the blue line is your uncatalyzed reaction for this exothermic process, and the catalyzed reaction might have shown the 2 transition states that we're forming and an intermediate here in this pocket. So this is where my intermediate would have been. This is where my transition state 1 would be. Here's where my transition state 2 would be for the catalyzed reaction. The uncatalyzed reaction has an activation energy that is this full height here on my diagram. So that's my activation energy. My catalyzed reaction has an activation energy, whoops, for step 1 here. So we say that's activation energy for step 1 for the catalyzed reaction. Step 2 would have an activation energy here for the catalyzed reaction. Since I've lowered the activation energies for the catalyzed process, we expect the rate or the speed of the chemical reaction to be increased. Let's try one more time, seeing if we can identify any intermediates or catalysts present in a chemical reaction. Let's consider ethene, a hydrocarbon with 2 carbons with a double bond between the 2 carbons, as it's being converted to ethanol. So ethene is the following molecule with a double bond between these 2 carbons. Ethanol is going to also be known as grain alcohol or drinking alcohol, CH3CH2OH, and it goes through a 3-step process. First of all, the ethene reacts with hydronium cations from an acid in a water-based system to form ethane. Actually, it's a cation that's similar to ethane and water, and then we end up with that cation reacting with a water molecule to form ethanol, or it's close to ethanol. It has an extra bond to hydrogen here, which will not be maintained. It's another cation, and that cation reacts with water to form the hydronium cation back, and we end up with having ethanol in the very end. So here's my ethanol that's formed. Here's the ethene that reacted at the beginning. Okay. Now, can you see any catalysts present? So a catalyst would be something that was there at the beginning of the reaction and reformed at the end of the process. So my hydronium ions from the acids were there to initiate this catalyzed reaction, and the hydronium ions were reformed at the end of the process. So as I have the hydronium ion catalyst reformed, it could be used again and again in order to produce this reaction. Now I can see that I have a few intermediates. So if I want to look at my intermediates here, let's go ahead and put those in green. So here's an intermediate that was formed in step 1 but consumed in step 2. So that's what I'm looking for, an intermediate. Something that wasn't there at the beginning is formed then consumed. And then I have an intermediate in step 2 that was formed and then consumed in step 3. So I actually have 2 sets of intermediates, and I have 1 catalyst here. That was the hydronium ions. So make sure you can identify when you have your catalysts as well as your intermediates. So here I've shown my catalyst in yellow and my intermediates in green for your reference. Now what I'd like you to do as a class is go ahead and consider the following reaction mechanism when we're looking at ozone again. Ozone reacting with chlorine gas to form diatomic oxygen and chlorine monoxide, and then chlorine monoxide reacting with ozone to form monoatomic chlorine and oxygen gas. Now with your class, I'd like you to pause the video and go ahead and decide which one of these answers gives you the correct overall reaction with the correctly listed intermediates and catalysts. Okay, so once your class has had a chance to do this, you should recognize that you have a catalyst that's chlorine monoxide that we talked about before that is regenerated at the end of this reaction, so it can be used over and over again and recycled to continue speeding this chemical reaction. So my catalyst would be Cl. My intermediate would be the chlorine monoxide that is formed but then consumed. Right? So if I'm looking at this, I have 2 possible scenarios. What I want to show is that I have 2 ozone molecules forming 3 diatomic oxygen molecules. The catalyst was there to begin with, the catalyst is there at the end. My intermediate is chlorine monoxide, and my catalyst is chlorine. So my best choice here would have been B in this case. So what we're seeing here is that chlorofluorocarbons, which are called CFCs, produce chlorine, and the CFCs produce chlorine by UV radiation, breaking them up, but the chlorine then can catalytically keep damaging our ozone layer, which is why we control the production and release of CFCs currently. Okay, so that's the end of our discussion on reaction catalysts and intermediates and factors affecting the rate or speed of chemical reactions. Next time we will be talking about equilibrium processes.